So let's start by looking at ratios where we compare part to part. So if we have a sum of money and we divide it into two parts, given a particular ratio, then we compare how large or small one part is to the other. So for example, if we have €900 and we want to divide it between John and David in the ratio 4:5, let's find out how much each should get. So €900 is going to be divided into two parts, and those parts are represented by the ratio 4:5. Okay, so the way we look at this, the way we answer this type of question is we find the total number of parts or shares, and we do that by adding the first and the second term. So 4 plus 5 gives us 9 parts or shares, and John will get 4 parts of the 9 parts, and David will get 5 parts of the 9 parts. So John gets 4/9 of €900, and so that's €400, whilst David will get the remaining 5/9 of €900, and that would be €500. And because we have 4/9 and 5/9 gives us 9/9, the whole amount, which is the €500. And if we just take a moment here, if we see the 4/9 and the 5/9, these are this 5/9 is the proportion of the €900 that David gets, and the 4/9 is the proportion of the €900 that John would get. And a proportion is different to a ratio in that a proportion is a comparison of a part, like the 4 or the 5, to the whole. And we can also express a proportion like 4/9 or 5/9 as a percentage as well, if we multiplied either of those by 100. Either of those proportions or fractions by 100 would get a percentage of how much the guys would get, a percentage of the 900. So let's look at the second example. How would we divide €1,200 into 3 parts in the ratio 2:3:1? So we're going to divide the €1,200 three ways, because we've 3 terms in the ratio here. And the way we approach the ratio problems is, the first thing always do is to add the terms, the 2 plus the 3 plus the 1, and we see that there are 6 parts. This €1,200 will be divided into 6 parts, but someone will get 2 of those parts, someone will get 3 of those parts, and the last person will get the remaining 1 part. Okay, so the divisions would be as follows. Someone would get 2/6 of the €1,200, that would be 400. Someone would get 3/6 of the 1,200, that would be €600, and the last person would get 1/6 of the 1,200, and that would be €200. Let's look at this third example then. A sum of money was divided between Laura and Jane in the ratio 5:2. That should be 5:2. If Laura received €165, remember she got 5 of the 7 parts. She received that was worth €165. What was the original sum of money? What is the 7 parts equal to? Okay, so anyway, look, how we approach this, as always, add the 2 terms. 5 and 2 is 7, these 2 terms here. And Laura got 5/7. Laura got the 5 parts, Jane gets the 2 parts. So Laura got 5/7 of the sum of money, and that was equal to 165. So 1/7 of the sum would be 165/5, because we divide both sides by 5. So therefore the sum of money is all the parts, the 7/7 of the sum, the original sum, is that 1/7 value times 7, and that's €231. So the total original sum was €231. Another example here now, the ratio of girls to boys on a school trip is 5:4. So for every 5 girls that travelled, 4 boys travelled. If 56 boys travelled on the trip, how many girls were on the trip? Okay, so the answer to look at this, first of all, just remind ourselves that the girl to boys ratio is 5:4, and we add the terms 5 and 4, so we know that there's 9 parts in total. And we're told that 56 boys travelled, and that refers to this 4 part in the ratio. So we know there's 9 parts in total, so 4 ninths of the total of the travellers is equals 56. Okay, so 1/9 must be 56 over 4, and the girls' value, which would be 5/9, must be equal to that 56 over 4 times 5. And let's look at our fifth example then. The ratio of girls to boys on the school trip was 5:4. How many girls travelled when 180 people travelled in total? Okay, so we add the terms. So we know that there's 9 parts to consider, 5/9 and 4/9, or 9/9. We'll have a look now and see. This time we're told that 180 people travelled in total. So that's our 9/9 of the travellers, that's all of them, must be equal to 100 and, maybe we'll call that 189 there, is equal to 189. So 1/9, divide both sides by 9, so this becomes 1, and this becomes 189 over 9. So we now know what 1/9 of the travellers were. So 5/9 then is the number of girls who travelled. So 5/9 of the travellers must be equal to 1/9 multiplied by 5, and that's 105. So if 189 people travelled, and the ratio of girls to boys was 5:4, then that means that 105 girls travelled. Okay, mortar used to plaster walls is a mixture of sand, lime and cement in the ratio 6:2:1. Sand, lime, cement. Okay, find how much sand is needed to make 60 kilograms of mortar. Well, we add the parts first of all. 6 plus 2 plus 1 tells us that there's 9 parts to consider, and the full mix was 60 kilograms. So 9/9 is a full mix, and that's 60 kilograms. So let's find 1/9, and that's 60 over 9. And the question is, find out how much sand. Well, which is the sand? The sand is the part of the ratio that is 6 parts. Okay, so that must be 6 parts, 6/9. Each ninth is 1 part. 6/9 amount of sand must be equal to the 1/9, 60 over 9, times 6, 40 kilograms. And again, a similar or same question, just further a bit. To mix an amount, Tom used 6 buckets of lime. How many buckets of sand did he use? Well, the ratio sand is to lime is to cement is 6:2:1. Okay, number of parts is 9. He used 6 buckets of lime. So two parts of the mixture, 2/9 of the mixture was equal to 6. So we'll go find out what 1/9 is equal to. That's equal to, divide both sides by 2, is equal to 3. And then we would need to know how many buckets of sand did he use. Well, the sand is 6 parts, 6/9. So we know what 1/9 is. So 6/9 must be our 1/9, which is equal to 3 times 6. So 6 times 1 over 9. And that's 6 times 3, that's 18 buckets of sand are used to keep the ratio maintained. Now we're going to look at the term proportion. We met proportion in the first slide of the video where we were saying that if money was to be divided into 2 parts, we were looking to see what proportion of the money each person would get. but we're going to use the word proportion in a different way here now, and we're going to look at two types of proportion. And the first type we'll look at is this notion of direct proportion. Okay, so if for example we have a number of apples and their cost increases or decreases in the same ratio, then the number and the price are directly proportional. We would say that, the number of apples is reflected, the price of the apples is reflected by how many apples you have in the same, if that increases in the same ratio, they're directly proportional. So, for example, if one apple is 80 cents, if the number of apples and the price of the apples are directly proportional, they both will increase one and you increase the other in the same ratio. 2 apples must be 2 times 80 is 160. 3 apples is 3 times 80 is 240. And, the ratio of that would be 1 apple is to 0.8. Okay? So here's an example of how we'd kind of consider direct proportionality. So if 8 apples cost €3.20, find the cost of 1 apple. Well, 8 apples is equal to €3.20. 1 apple must be equal to €3.20 divided by 8. 1 apple is 40 cents. Or on the other hand, we might be asked to find how many apples can be bought for €1. Well, €3.20 buys us 8 apples. So €1 buys us 8 divided by €3.20. We've divided both sides here by €3.20. So €1 would kind of buy us 2.5 apples. And this way of finding the value of one variable to the other, one variable to the other, or one variable to the other, is known as the unitary method. And we'll look at another direct proportion example. A car travels 120 kilometres on 9 litres of petrol. How far would 15 litres of petrol take it? Well, we need to compare one variable with the other. So 9 litres takes us 120 kilometres. So divide both sides by 9 to find how far 1 litre would take us, and that would take us 120 over 9 kilometres. And if we multiply both sides by 15, we'll find how far 15 litres will take us. We might be asked how many litres are needed to travel 280k. Well, again, now we're looking for our litres here, so we'll keep our litres to the right. Here we were looking for our kilometres, and we kept our kilometres to the right. So what you're looking for is what's right. This might be one way of remembering how to approach these at the beginning. But anyway, we set up this time 120 kilometres equals 9 litres from the beginning of our problem. So 1 kilometre, divide both sides by 120, we only would need 9 120ths of a litre. So to find how many litres we need for 280 kilometres, just multiply both sides by 280, and we see that 21 litres in this car would take us 280 kilometres. So we've looked at direct proportion, where the increase in one variable, if the increase in one variable resulted in an increase in the other variable in the same ratio, then they were directly proportional. Now we'll look at inverse proportion, okay? And two quantities, or two variables basically, are inversely proportional if an increase in one causes a decrease in the other in the same ratio. Okay, so just an example so you can visualize that. A car takes 4 hours to travel 200 kilometers at a speed of 50 kilometers per hour. Each hour does 50 kilometers. 4 hours later, it's traveled 200 kilometers. If we increase the speed to 100 kilometers per hour, then we're going to get there faster, and so we're therefore decreasing the time taken to travel the same distance at 2 hours. So speed and time are inversely proportional to each other. So if you increase the speed, you decrease the time, or if you're going to take longer to get there, then you're increasing the time, you're going to decrease the speed, inversely proportional. And when we consider inverse proportion, we need to, there's two types of problems that we'll look at. The first, we call them best buys. So if we increase the size of the washing powder boxes, which makes them more expensive, but often it's reducing the actual price per kilogram of powder in the box. So the bigger box you buy, you're generally getting your washing powder for less per kilogram. And the second example we'll come to is, I call them the man hours examples, where we increase the number of people to do a task, and by increasing the number of people to do a particular task, we reduce the time taken to do the task. So if we've 4 guys building a wall, it takes them a day. If we put 6 guys on the job, it's going to take them less to do it. So here's a Best Buy example. We have 2 sacks of potatoes. One is the value pack, 3 kilograms of potatoes is €2.94. The bigger pack is 5 kilograms, and that's at €4.80. So that's the family pack. So let's find the cost of 1 kilogram of potatoes in this pack here. So 3 kilograms is cost $2.94. 1 kilogram must be $2.94 divided by 3. It's 98 cents per kilogram in this bag. Whereas the cost of a kilogram of potatoes in the family pack, we 5 kilograms for €4.80. So 1 kilogram is 96 cents per kilogram. So actually, even though you're paying more for the bag, you're getting your potatoes 2 cents cheaper per kilogram. So that asks the question then, which gives better value? Well, the family pack is better value as it's 96 cents per kilogram rather than 98 cents. And a man hours example then, if 9 men can build a wall in 8 days, how long will it take 6 men? Well, the way I approach these types of problems is I look at, I call the job total in man days, where I multiply the number of days by the number of people, okay, or the number of hours or minutes, whatever it is, by the number of people performing the tasks. So I've 9 by 8. To do the job, it takes 72 man days. So we could leave 1 man on the job for 72 days, or we could put 72 men on the job on the same day and then have it done at the end of the day in 1 day. Okay, but we're looking to see how long it takes 6 men to complete the job. So we simply divide the 72 man days by the 6 men or man, so they'll cancel out, and that will give us 72 over 6, 12 days. And we'll just finish this video then by just looking at different ways of working with tidying or simplifying ratios. Often this is at the beginning of the chapter in the book, but I like to leave it till the end because I hope that work with ratios has made a bit more sense to you when you can see their application. Anyway, the first example, you might often be given a ratio with large numbers, 24 is to 16, and you might be asked to reduce it to its simplest form. So, as with fractions, the way we can reduce the terms in the ratio to its simplest form is we find the highest common factor of the 2 terms, and that's 8, and we divide 8 into both. 8 goes into 24 3 times, and it goes to 16 twice. So the ratio 24 is to 16 reduced to its simplest form, or is the same as 3 is to 2, and I can't actually reduce that any further. Sometimes we're asked to express ratios in whole numbers, and we like to, if we can at all, work with ratios where the terms are whole numbers. Okay, so we might be given something like express the ratio 1 and 1/4 is to 2. Okay, so the way we do that is we'll we'll convert this mixed number into the fraction. So 4 times 1, sorry, is 4 plus 1 is 5 over 4. And we just rewrite the ratio 1 and 1/4 to 2 is the same as 5 fourths or 5 quarters is to 2. Okay, so now we're looking to get rid of the 4. So we multiply both sides by 4. And these 4's will cancel out, and 4 2's are 8. So the answer is 5 is to 8. 1 and 1/4, 1 and 1/4 to 2 is the very same as 5 is to 8, but at least this time we have whole numbers to work with. Sometimes we're asked to find the missing number, so we're given a ratio 2 is to 3 is equal to, or the same as, 4 is to, find the missing number. And here's the trick, or a way of doing these, the quick way really, is to write the first ratio and write the second ratio directly underneath it, okay? And then you cross multiply, so you say 2 times the value you're looking for is equal to 4 times 3. 2 times the value you're looking for is equal to 12, so divide both sides by 2. They cancel out, the value you're looking for is 6. So 2 is to 3 is equal to 4 is to 6. They're the same ratio. This is a reduced version, or simplest form version of that one. Sometimes we're asked to express ratios in their simplest form, but we're given different units within the ratio. So we've 20 cents and €1. We should have it either both in euros or both in cents. But in this case, we'll make sure the units are the same on each side, and we'll go with the cents. So we'll rewrite 20 cents is to €1 as 20 cents is to 100 cents. Okay, and then to reduce that to its simplest form, the highest common factor of 20 and 100 is 20. Divide both sides, and we get 1 cent is to 5 cents. And that means that our ratio is 1 is to 5. And we'll finish now just with a menu example. So to make lemon ice cream, to make 6 servings of lemon ice cream, we need 10 egg yolks, 200 grams of sugar, 500 millilitres of juice, and 400 millilitres of cream. And we might be asked, how many egg yolks is needed to make 9 servings? Now, we know that 10 egg yolks makes us 6. So we write our yolks is to servings ratio. That's 10 is to 6. They're asking us to find how many yolks, we don't know that, so we'll call it x, is to 9 servings. We'll write one over the other like we did in a couple of examples ago. And the trick again is to cross multiply. So 6 times what we're looking for is equal to 9 times 10. So what we're looking for, if we divide both sides by 6, must be equal to 9 tens are 90 divided by 6, 15 yolks for 15 yolks for 9 servings. And then we may be asked, if 25 egg yolks are used to make this lemon ice cream, how many servings would that be equal to? Well, again, we'll look at our egg yolks to servings ratio, and it's 10 is to 6. Okay, so 10 egg yolks. Now they've told us 25 are used to make an unknown amount of servings, so we're writing one over the other, and then we're going to cross multiply. So 10x is equal to 6 by 25. So x is equal to 150 over 10. So that will give us 15 servings if 25 egg yolks are used, if we're to maintain this servings to ingredients ratios.